Welcome back. In this video, we will be looking into nonlinear classification with the use of kernels. We will go over linear kernel, polynomial kernel, and RBF kernel, their hyperparameters and their impact. In the end, I'll wrap up the theoretical side of SVM, and now let's get started. Before, we saw data that was linearly separable, either clearly linearly separable or separable with the use of soft margins, so with the help of some certain amount of slack. But if we look at the example on the left side, the green triangles are in the middle, so no matter where we would draw the line, half of the blue squares would be misclassified, and potentially some of the green triangles would be misclassified as well. If you look on the right side, what we did to the data was that we introduced a new dimension. And in this case, for this very simple example, the new dimension x2 is just simply x1 squared. I hope you can clearly see the shape of the function. And for this simple example, it solved our problem. So all the green triangles are now on one side, and we can draw a hyperplane between them to clearly separate these two instances from each other. Now there are many shapes of data that are non-linearly separable, and from a two-dimensional space we can talk about a donut shape, so that those are two circles that have the same center, and it's like an outer circle and an inner circle. There is no way we can draw a line to separate them. There is also commonly used example of crescent moons, and we will also look at some crescent moons in the coding example in the last video. Or we can have some intertwined spirals or any other data that would commonly be present in a data set might not be linearly separable. So what we did in this example was that we introduced a new dimension, but introducing a new dimension and computing it for all the data points can be very expensive and can not always lead to a separation that would actually help us. So the more dimensions we introduce, the slower the algorithm gets. And that's why we would like to use a kernel function or a kernel trick. And a kernel function computes the similarity between two generic vectors, xi and xj. It transforms them, so it uses this transform function without actually computing the transformation. So instead of computing the dot product of the two transformed vectors, we call a kernel function k on xi and xj, and instead of manually mapping the data into higher dimensions, we use a kernel function to compute the dot products in that space without explicitly transforming the data. There are multiple types of kernels. We will be looking at linear kernel, polynomial kernel, and radial bias function kernel. First, the linear kernel is simply a dot product of the two vectors. It is the simplest of the kernels that we will be looking at today, and it is equivalent to the standard SVM decision function. This is the simplest of the kernels and has some advantages and disadvantages that we will go over in the end. Now, if we look at a polynomial kernel, this is equivalent to adding many polynomial features, but we don't actually need to add them. Instead, we call the kernel function and it computes it without explicitly transforming the data. As we can see, we have a gamma times the dot product of the two vectors plus r, which is some certain coefficient, and it is exponentiated over the power of d, which is a degree of the polynomial function. And if we set d equal to 1, then it is equivalent to the linear kernel. Below we can see two examples of different values of the hyperparameters and the effect that they have. on the separation. As we can notice, if we look at the data in 2 dimensions, the separation is no longer a straight line because it added more features, so we added more dimensions. We will go over the impact of the hyperparameters on the results of the functions in the end after we look at the last kernel. Now, why we would like to use a polynomial kernel is if we need to capture curved decision boundaries. The line is no longer a straight line, but it is curved. And it is useful when the data has some sort of polynomial relationships. The last kernel that we will look at is radial basis function, or a Gaussian kernel, and it maps the problem space into an infinite dimensional space. So we can again see our gamma variable, and we can see our r, but instead of on the power of d, we are now using it on the power of 2, and this entire thing is the power of our Euler number e. Again, below we can see some examples of different values. This time we are changing the value of c. You can see that the higher the value of c, the more curvy it gets. Note that the RBF kernel is the default kernel in sklearn, so if you do not specify which kernel you would like to use, then it would just use the RBF kernel. Now let's look at the hyperparameters that we went over. Hyperparameter c is, if you can remember, we already saw it in our linear classifier. So it affects the size of the margin. We saw it in our soft margin SVM. We were talking about the c together with the slack variable zeta. Another hyperparameter is gamma, and that influences the curves of the boundaries. If we have a high c and high gamma, then it will risk to separate the points into their separate regions, which will result in overfitting. If your model is overfitting, try tuning down c or gamma or both of them. We also had the hyperparameter d, which influences the complexity of the model because it's the degree of the polynomial. So the higher the degree, the more complex the model is. And just be mindful, because we are talking about a degree of a polynomial, polynomials look differently if they have an even degree or odd degree. So be mindful that the difference between 100 and 102 might be different from 101, just because one of them is an even degree, one of them is an odd degree, even though the numerical difference between them is not that big. And the last hyperparameter that I will mention here is the r. In scikit-learn it is called coef0, and you will also see that in the coding examples. And the complexity of the curve increases when r is not equal to 0. So if r has a different value, then we end up with a more complex model. And the higher values of r give more weight to the lower degree terms of the polynomial. So if you end up playing a lot with the coefficient, then maybe you should switch to the RBF kernel instead. Now let's look at the comparison of the kernels between each other. The linear kernel is used when the data is already linearly separable, as the only thing that we are doing is the dot product, and it is relatively simple, so it is relatively fast compared to the other kernels. And it works well if the data is in high dimensional spaces, since we are not adding more dimensions. The polynomial kernel lies performance-wise between the linear kernel and the RBF kernel. It maps data into higher degree polynomials without explicitly transforming the data. It allows for a curved boundary with the use of the degree d. last not least, the RBF kernel, which again is the default kernel that the scikit would use. And this one maps the data into an infinite dimensional feature space. And it works well with complicated and non-linear decision boundaries, but because it is more complex than the other ones, then it is slow. There are more kernels that are available in scikit-learn. If you would like to look at that, then you can look into a sigmoid kernel, which is inspired by neural networks, but is not as commonly used as the RBF kernel. Now let's just do a quick summary of the entire support vector machines. We went over linearly separable data, we went over soft margin, we went over multi-class classification and the kernels. Overall, support vector machines on classification perform very well on high dimensional data. They are very flexible as of what type of data and what shape of the data it can work with, depending on then our choice of the kernel. And it is quite powerful as it is very versatile. However, we should keep in mind that some of the kernels, as for example I mentioned, the RBF, the radial basis function kernel, can perform quite slowly. The whole SVM is vulnerable to scaling, as we saw in the beginning, and it might require therefore pre-processing. It requires hyperparameter tuning. It might result in overfitting, as we saw in this and the previous video on the soft margin as well. And that is why we need to be cautious about choosing the values for C, for gamma, for the degrees. That's it for the theoretical side of SVMs. I hope this video series gave you a clear understanding of the base concepts of SVMs, when and why we use them, the kernels, how they work, and which one to choose in what situation. If you have any questions, you can drop them in the comment section, and I'll see you in the next one.